Bismillahirrahmanirrahim. So the next will come to week number 10. So this is the continuation of delay. So this is from the book chapter on chapter number 4, which is delay. So we have discussed some of the material in week number 9. This is week number 10, and we come to this very important topic called logical effort. So this is the outline of presentation: a logical effort, delay in a logic gate, multi-stage logic networks, choosing the best number of stages, and we will go through several examples and a summary. So imagine that you are a chip designer. So you have several questions to answer. The first one is what is the best circuit topology for a function? So for example, if you want to implement an adder, what is the best combination of logic gates, and how should you connect those logic gates for an adder? Because how you connect the circuit will define your speed or your delay. It will also define your power consumption and all the important things in the VLSI world. Then the second question is how many stages of logic should I use to get a certain value of delay? Third is how wide should the transistor be? So what should be the width of a transistor? Okay, so all these questions are answered by what is called a logical effort. It is a systematic method to make these decisions. It uses a simple delay model, and it allows calculations, you can say, for not only getting the number of stages, but also the sizes of transistors, and tells you which topology is best and all these things. So we can understand all these things with examples, so it will become clear. So imagine this is a motivating problem. So this is from the book. Ben Bittidel is a memory chip designer for Motorola. This is a certain microprocessor, microcontroller. As an embedded automotive processor, helped Ben design the decoder of a register file. So here we have the register file. The register file is 32-bit wide, so it has the width 32 bits are stored, and this is you can say location 0. This is location 1, and so on. This is location 15. Okay, so 16 locations, and for 16 locations we need a decoder. A decoder is there to select a location. So a decoder is a circuit which has 4 inputs, so A 3 down to 0, and this is just the inverted set of inputs, so both are available. So a decoder is a circuit. This is basically what is called a 4 cross 16 decoder, 4 input lines and 16 output lines, and each of the 16 line is responsible for selecting a location. and I told you that every location is 32 bits. Sometimes these locations are called words. So we have 16 words that are stored in this register file. A register file is a very important element that is found in your computing systems. It is used by the processor frequently to store the data for calculation. So for example, if a processor implements this equation, a is equal to b plus c, so maybe the a is mapped to location 16, so it stores the result of 16. B may be mapped to location 0, and c may be mapped to location 1. So what it does, the processor accesses these locations. Maybe in the location 0 we have 10 stored, and maybe in location B we have 20 stored. So after the summation it will have 30 stored. Okay, so this is frequently used by the microprocessor. A register is very important element of a computing system. So we need to the problem is we need to design a decoder in such a way that it should be fast. Okay, how many stages should be used in the decoder, how many stages of logic levels, how large should each gate be, and how fast the decoder can operate. So this is like a motivating real world problem. So we need to answer these questions very, very systematically. Okay, so after some slides, a couple of slides, we will come back to answer these questions for the decoder. But we need to develop some equations before we can answer these questions. So the first thing is we want to represent delay of a logic gate in a fashion which is process independent. What is meant by process independent? It should not depend on, for example, if the transistors are implemented in 65 nanometer or 90 nanometer or 32 nanometer technology. We want to define the delay such that it is independent of the underlying manufacturing process. So we define the delay D. This we call normalized delay. So we want to define normalized delay as D absolute divided by tau. So D absolute is the delay that you measure in absolute units of time. So this is what you measure, and tau is basically the delay. It is equal to 3RC, 3 times R into C. This is basically the delay of minimum size inverter. So remember that an inverter had, if you remember, an inverter had PMOS and it has an NMOS. These two are connected. So we have here the VN, here we have the V out. Okay, so remember that this was size 2, this was size 1. So if you consider the capacitances at the input, 2C is coming from the gate of PMOS, C is coming from the gate of NMOS, so the input capacitance is 3C. Same goes from the output capacitance at the nodes. So this is 1C, this is 2C, so it is 3C. So the tau of a minimum size inverter is 3C at the output. Okay, so that's why it's 3C. So what you do is you normalized delay is basically the delay in picoseconds, for example, divided by the delay of a minimum size inverter. So some of the typical values of inverter of tau are this. So it is 3 picosecond in 65 nanometer technology, and it is 60 picoseconds in 0.6 micrometer technology. Delay has two components. We have already seen one was the one was the effort delay, and the other one was the parasitic delay. So the delay has two components, F and D, where F is the effort delay and it is equal to G into H, and this effort delay is also called stage effort. So you can call it effort delay or stage effort. It is basically G into H. Again, there are two components. One is G, which is the logical effort, and the other is H, which is the fan out. What is logical effort? Logical effort is basically the ability of a gate to deliver current. So, for example, for inverter, G is always 1. Okay, it is an inverter can an inverter is used basically as a reference. So everything we will compare to an inverter. So inverter is the baseline. That's why the logical effort of inverter is 1. Then we have the electrical effort, and sometimes the electrical effort is also called fan out. So electrical effort is also called fan out. So it is basically the output capacitance C out divided by the input capacitance. Then we have the parasitic delay, which represents a delay of a gate driving no load. So it is basically the delay of the internal gate set by internal parasitic capacitances. This is basically a plot of the normalized delay. So on the y-axis we have our normalized delay, and on the x-axis we have fan out or electrical effort. So we have here our electrical effort, and then we have two curves, two plots. One is for a 2-input NAND gate and the other is for inverter. You see that the inverter, when there is no load, so no load means the fan out or H is equal to 0. When there is no load, H is equal to 0. So the delay is basically G H plus 1. So delay is, we have a G of 1, we have a H of 0, there is no fan out, and we have a P of 1. So the normalized delay is 1. So that's why it starts at 1. And for the NAND gate, the delay is G H plus P. Okay, so so the delay is this one. So again, when there is no load, so it is 0 plus the parasitic delay of a NAND gate is 2. So it is equal to, D is equal to 2. So you see this 2. Then if you increase the fan out, we have these two curves that goes on different slopes. So the slope of NAND is higher than the slope of the slope of NAND is higher than the slope of inverter. We will come to this one, why the G is 4 by 3. Okay, we will come to this one, but this is a sort of a graph that shows that everything is measured one relative to inverter, and second we have a linear relationship between the fan out and normalized delay. Okay, so if you increase the fan out, the normalized delay will be affected the most. The parasitic capacitance, the parasitic delay is sort of normal, so it depends how many things you connect to the gate, and the delay will increase linearly with the number of gates that you connect to the output of a certain gate. So what about NOR gate? We will discuss all these here. So remember that G is 4 by 3. Now we are going to understand why it is 4 by 3. So let's come first to the definition of logical effort. A logical effort, the logical effort is the ratio of input capacitance of a gate to the input capacitance of an inverter delivering the same output current. Measure the delay, measure from so let's understand this with examples. So let's consider first the inverter. So we know that the size of PMOS is twice the size of NMOS, and this is the value of K in RC model. This is the value of K for N, and so this is the gate capacitance become 2C. Here it becomes C, both are in parallel, so the Cn is basically 3. And because inverter is our reference, so G is basically 3 divided by 3, which is 1. Okay, so the logical effort of a inverter is always 1. Let's come to the logical effort of a 2-input NAND gate. So this is a 2-input NAND gate. You can say 2-input NAND gate. So remember that when we have parallel combination, the size does not change. So the size for PMOS is 2, and the size for NMOS is twice the size of unit NMOS, which is 2. So they are in series, so it becomes 2. Now what is the input capacitance? The input capacitance is 2C from here and 2C from here when I look into my input B, for example. Even if I look from the input C, again it is 2 plus 2C, so it is 4C. So my Cn of the gate is 4. And what is my Cn for inverter? So basically G is Cn gate divided by Cn inverter. So it is 4 by 3. Okay, I hope it is clear. Now let's come to 2-input NOR gate. The 2-input NOR gate has the pull down network of NMOS in parallel. That's why the size does not change compared to a unit inverter. But the PMOSs are in series. That's why the sizes are double the size of PMOS used in a unit size inverter. So that's why it's 4. Now if I look into the input, I have a capacitance at the gate 4C and 1C, which is 5. And the unit inverter has an input capacitance of 3. So that's why the logical effort of a 2-input NOR gate is 5 by 3. This is basically a table for which shows what is the logical effort for some common gates with different number of inputs. So for example, for an inverter, we already discussed that it is 1. An inverter has always a single input. If we consider NAND gate, so it is 4 by 3 for this is if the inputs are 3, then it is 5 by 3, 4, 6 by 3, and for n inputs the delay of a NAND gate is n plus 2 divided by 3. Similarly for NOR gate it is 2n plus 1 divided by 3. And there are other gates. If you want, you can draw these gates and you can calculate the logical effort for your understanding. Now interesting is the case of this MUX, MUX or tri-state, which the logic effort is constant at 2. But if I go to the next table, this is the table for parasitic delay P. So remember that delay was GH plus P. So P is the parasitic delay, the internal delay of a gate. So in case of the MUX, you see it is dependent on the number of inputs. Okay, so the logic effort was constant, but the parasitic delay is a parameter that depends on the number of inputs. So you can practice with some of the gates if you want to better understand the parasitic delay and logic effort. For example, you can draw a 4-bit XOR gate and calculate the logical effort and the parasitic delay. Let's come to another example, which is the example of a ring oscillator. So the example says estimate the frequency of an in-stage ring oscillator. A ring oscillator is basically inverters, a lot of inverters that are connected in cascade. So for example, here we have n inverters that are connected in cascade, and then the output from the last one is feedback to the input of the first one. So what is the logical effort? The logical effort, because they are inverters, the logical effort of the gate is 1. What is the electrical effort or the fan out? The fan out of each one is 1. What is the parasitic delay? It is 1. And then what is the stage delay or effort delay? It is G into H plus 1. Okay, so you see it is 1, 1, 1 and 2. Okay, and so the stage delay is basically 2. So you see all these. And now what is the frequency of oscillation? Now for the chain of inverters, if I apply a certain input 0, okay, for example, let me take this small example. Okay, so if I apply 0, it becomes 1, it becomes 0. Okay, so then it has this feedback loop which again applies it. So the output, if you want that the output should go from 0 to 1 and then 0 to 1, it requires 2 times n, where n is the number of inverters. So it requires this much iterations, 2n iterations, and this is basically one period. So if we want to measure the period, it is from here to here. So it requires 2n iterations. So we can say that our time period is basically d, which is our stage delay, into 2n. So we can say 2 into 2n is basically 4n, and this is our period, or frequency is 1 by capital T. So if you plug in all these values, you get 1 by 4n as the frequency. Now here is a statement. Our 31 stage ring oscillator, so which has 31 inverters, in a 0.6 micrometer process, has a frequency of 200 megahertz. Okay. Let's come to another example. So in this example, we have an inverter which is driving the inverter 2, 3, 4, 5. So this is sometimes called fan out of 4 or FO4. So what is the logical effort? The logical effort for a NOT gate is 1. What is the electrical effort or fan out? So it is 4, because this inverter is driving 4 other inverters. So it is 4. What is the parasitic delay? Is 1. What is the stage delay? It is G into H plus 1, which is 5. So we plug in all, we get the stage delay of FO4 inverter is 5. In the FO4 delay, in a 0.6 micrometer process is 300 picosecond, and in 65 nanometer process it is 15 picosecond. Okay, so let's come to multi-stage logic networks, where you have multiple levels of functions. So for example, this is a multi-stage circuit. The first stage has an inverter. This is stage 1, this is stage 2, this is stage 3, this is stage 4. Sometimes these are called logic levels. Okay, so we have to generalize our definitions for G, H and F. So we have to define the path logical effort, capital G, as the product of all logical efforts. We have to define the path electrical characteristics, electrical effort, or fan out, as capital H is the C out path, which is the final output from the multi-stage network, divided by Cin path, the input to the multi-stage network. And the path effort, capital F, is basically the product of all the stage F and G. So it is basically stage wise product of G and H. Okay. Now here are some values. For example, G for an inverter is 1. What is H? H is, here we have the capacitance X, and here we have the input capacitance 10 because of this, so it is X by 10. Similarly, for NOR, 2-input NOR gate, we already calculated that the logical effort is 5 by 3, and here we have the capacitance Y, and the H2 is Y by X, output by input. Here this is a 2-input two-input NAND gate, so the logical effort is 4 by 3, and here we have Z divided by Y. For 4, we have an inverter, we have the logical effort 1, and H4 is the output capacitance, which is 20, divided by the input capacitance, which is Z. Okay, later in the coming examples, we will see how we can calculate the value of X, the value of Y, and the value of Z. So we will solve example to come up with how we find these values. So again, the new thing is this one on this slide. Can we write capital F as F capital G into H? So the answer for this is no, because of this one. Okay, this is the proof that capital F is not always equal to capital G and capital H product. This is due to branches. So imagine you have an inverter which drives 2 other inverters. So this is our inverter 1, this is our inverter 2, this is our inverter 3. So inverter 1 is driving inverter 2 and inverter 3. Now at the output of inverter 2, we have a capacitance of 90, and similarly at the output of inverter 3, we have a capacitance of 90. So what is the capital G? Because these are inverters, so all the logical efforts are 1. Okay, so if I say G1 is 1, G2 is 1, G3 is 1, and the product of all these capital G, G1, G2, G3, this is 1. What is capital H? Capital H was defined as C out divided by Cn of the path. So C out is 90 divided by Cn 5, which is 18. So this is the capital F. What is G into H? G into H is basically 18. Now let us calculate what is H1. H1 is basically the fan out of this one, which is, what is the capacitance here? The capacitance here is basically 15 from inverter 2, 15 from inverter 3 divided by input is 5. So we get 6. Similarly for the other one, H2, so H2 is 90 divided by 15, which is 6. And if we find capital F is G1 into G2 into all these things, we get 36. Okay, so you see it is 36 and it is 36 here and 18 here. So these two are not equal due to branching. So which is the correct one? The correct one is the value of 18. So we have to introduce a branching factor which accounts for the branch capacitances, and this is equal to B. Small b is capacitance on the path plus capacitance of the path divided by capacitance on the path, and the capital B is basically the product of all it's the product of all small b's. Okay, so now we can we can change the formula of capital F to include the branching factor, which is which is F into G into B into H. So let's apply this definition to that example. This is 15, then we have another inverter which is 15, then we have another inverter which is 15, we have capacitance of 90, capacitance of 90. Okay, so for example, this is our on path and this is our off path. So B is equal to the capacitance in on path, which is 15 plus 15 . So this one, so let's say this is our inverter 1, this is our inverter 2, this is our inverter 3. So this 15 is coming from inverter 3, this 15 is coming from inverter 2 divided by 15, which is coming from inverter 2. So B is equal to 2. And because we have a single branch, then capital B is 1. Okay, and just have a correction. The capacitance of this inverter was 5, not 15, but this does not affect the value of small b or capital B. So if we go back to this example, now if we say that capital F is basically capital G, capital B, capital H, then capital G is 1, capital B is 2, we have calculated this, and capital H is 18. So now it is 36. So the correct answer is 36, not 18. So if I note this correction, it is the correct value is 36, not 18. So for correct value of F, we have to include B in our calculation. Okay, so this was the branching effect. Now let's develop some other formulas that we will use. So the path delay is defined as D of F. Capital D of F is summation of all the Fi's, which is the logical effort delay, Then we have the parasitic delay, which is capital P. It is the summation of all T's. Then we have path delay, which is capital D is df plus P. Definitely you will understand these with examples, so don't worry if it's looks like a lot of formulas. When you use it, it will become clear. Now let's come to another very interesting result, which is that in order to design fast circuits, okay, we need the delay to be minimum, and the minimum delay is computed when each stage of your circuits bears the same delay effort. So we call this F cap. F cap is basically Gi of each stage into Hi, the fan out, and this is equal to capital F under nth root. So raised to the power 1 by n, or you can say nth root. So we can write this one very interesting and important formula in the red, which is the fastest delay is basically this one. N is the number of stages, F is capital F is your effort delay, plus P is your parasitic delay. So this is one very important formula that we will use. So this is a key result of from the logical effort. Find the fastest possible delay. So this gives you the fastest possible delay, and this does not require calculating the gate size. So you can calculate the fastest delay without going into without needing the gate sizes. Remember, you can calculate the gate sizes after coming up with the minimum delay. So all these things will become clear in examples. Here we are just introducing the formulas, and when we use it, you will understand how these formulas are helpful. So how wide should be the gate? It is a result from the minimum F cap. So it is G into C out by Cn, which is the fan out, and from here you can find Cn is basically Gi C out of the stage divided by F cap. So basically you have to work backward and apply the capacitance transformation to find the input capacitance of each gate. Okay, so again, I told you that you will not understand these formulas until and unless we solve some examples. So let's try to solve this example and understand. So this is example 4.13 in the book, and we are given this three-stage circuit. So this is stage 1, this is stage 2, and this is stage number 3. We are given the output capacitance and the input capacitance. So it is basically Cn is basically Cn is equal to 8C. Okay, so what is the question? The question is select the gate sizes X and Y. X is the size of NAND gate and Y is the size of NOR gate for least delay from A to B. So this is A, this is B, and the path is highlighted in blue. So we have to determine for least delay what is the size of gate X and gate Y. So again, what is the logical effort? The logical effort is this is for 4/3. This is for NAND gate. Let me write here. So small g, small g is 4/3. This we have discussed already. Similarly, so this is our G1, G2 is 5/3, and G3 is also 5/3. If you are unsure about this, you can use these formulas. So for NAND gate, it is n plus 2 divided by 3. So when n is equal to 2, it is 4/3. When n is equal to 3, it is 5/3. Okay. Similarly for NAND, for 2 input NAND, it is 5/3. So you can use this formula and this formula if you don't remember these values. Okay, so we multiply this is G1, G2, G3, we get 100/27. what is the fan out or electrical effort? It is basically C out, which is 45 by Cn, which is 8 from the first NAND gate. What is the branching factor? So the branching factor is, if we consider, let's say we call this point, let's say this point is, for example, if we call this point D, and if we call this point E. So at point D we have a fan out of 3, and at point E we have a fan out of 2. So the overall branching factor is 6. The path effort, capital F, is G cross B cross H, which is 125. This is the total path effort, and we can find the best stage effort, F cap, as under root 3 of F. Why 3? Because we have n is equal to 3 stages. Capital N is equal to 3 stages. What is the parasitic delay? So this is also from the table. The parasitic delay for 2 input, NAND gate is 2 plus 3 plus 2. Again, let me remind you the parasitic delay. It was so this is the table for parasitic delay. Okay, it is proportional to n, the number of inputs. Okay. Okay, and finally the delay is so the final delay is capital D is N F cap plus P. So N is 3, F cap is 5, and capital P is 7. So it is equal to 22. And basically and what is this thing? So here the delay is represented as a fan out of 4. So one fan out of 4 delay is 5. So 22 divided by 5 is basically 4.4. Okay, so this is the minimum delay for the circuit. Now, using this minimum delay, we want to find y and x, and y and x are our gate sizes. So we start with y, and the formula used is this one. Let me show you the formula. This one, Cn at any stage is equal to the logical effort Gi multiplied by C out of I divided by Fk. So I can write this formula as Cn is equal to Gi. So Cn of I is equal to Gi into C out I divided by F cap. So C out is 45, okay, from here, and Gi for a 2 input NOR gate, so 2n plus 1 divided by 3. I think this was the formula. So we have 2 into 2 plus 1 divided by 3, which is equal to 5 by 3 for a 2 input NOR gate. So 5 by 3 is our Gi, and divide by F cap. So F cap from the previous slide is 5, so we get 15 as the size of our transistor. So this means that this is 15 and this is 15. So what is the equivalent capacitor seen at this point? Here the capacitance seen will be capacitance seen will be 30. So let's calculate the X. Again, C out at stage number 2 multiply by Gi of the NAND gate. 3 input NAND gate Gi is this one. You can use the formula also, and then divide by F cap, so it is 10. So this is 10, 10, 10. So now we have the sizes of all the gates, but this is not the end of the story, because we want what is the size of PMOS. So P is for PMOS and N is for NMOS. So what are the relative sizes? So remember that Y is 15 here, so it is divided as this, that the PMOS size is 12 and the NMOS size is 3. Why? Because in a NOR gate the NMOS are in parallel. So here we have 2 NMOS A, B. They are in parallel, and then we have two series. Okay, here is your output. So in order to size it 15, the size of this one will be 3, this one will be 3, and this one will be 12, this one will be 12. So if you look, for example, into the input A, the 3 plus 15, 3 plus 12 will give you 15. And the same story goes for how this comes out to be 4 and this comes out to be 6. So you basically have to divide the 10 according to the rules that you already know. This one was 8. So this is a complete example which shows how you can calculate the minimum delay for the entire circuit. And remember, while calculating the delay, we do not need the sizes of gate. Once you have the minimum delay, then you can work backward from the output of the circuit towards the input of the circuit, and you can calculate the gate sizes and the NMOS and PMOS sizes from that.